Now that we know what the logarithm is, let's see how it is used in real-life examples of compressed scales. A familiar example is the Richter scale used in measuring the magnitude of earthquakes. Direct measurement of earthquakes is done by seismometers, which record the relative intensity of ground movement. The graph to the right shows a typical year of earthquakes measured by relative intensity. Based on this graph, about how many earthquakes occur in a typical year. Each dot represents an earthquake, so we could try to count the dots. 1, 2, 3, 4, 5, and I could see that there are some very close to the x-axis. I might guess that there are about 20 or so earthquakes in a year. This graph gives the impression that there were only a few earthquakes over a year, but in fact, there were thousands. The problem is, most earthquakes have a relative intensity below 5 million, and the y-axis scale goes up to 140 million. This means most earthquakes blend in with the x-axis. If we measure earthquakes by magnitude rather than relative intensity, we obtain the following graph. Notice we could see many more earthquakes than we could see in the previous graph. These two graphs help us see how the compressed scale using the logarithm makes the difference among earthquakes more easily discernible. To convert to magnitude, we find the log of the relative intensity. This means if the relative intensity of the earthquake was 100, the magnitude would be 2. Of course, we might be given the magnitude and want to know the relative intensity. In that case, we will want the exponential form of this equation. Recall, to go from logarithmic form to exponential form, a 10 will replace the log, and the variables will flip-flop. So the exponential form equivalent to this logarithmic form is relative intensity equals 10 to the magnitude. The following table provides information on interpreting the Richter scale in practical terms. Notice the vast majority of earthquakes have a Richter magnitude of 2.5 or less. That is a relative intensity of 10 to the 2.5 or less, which is about 316 or less. No wonder we weren't able to see these earthquakes on the original graph. In fact, even the 30,000 earthquakes per year with magnitude between 2.6 and 5.4 would be hidden on the original graph. Example 3. If an earthquake has an intensity of 6,700, what is its magnitude? To find this, let's review the formula for magnitude above. Magnitude equals log of relative intensity. So to find the magnitude of this earthquake, we will take the log of its relative intensity. That is the log of 6,700. Remember, if we are taking a log of a power of 10, all we need to do is count its zeros. The log of 1,000, for example, will be 3 because there's 3 zeros. The log of 10,000 will be 4 because there are 4 zeros. The log of this number should be between 3 and 4 since 6,700 is between 1,000 and 10,000. To find a more accurate approximation, we need to use our calculator. Once again, you will need a scientific calculator or a calculator that has a log button. When we type log 6,700, we get approximately 3.8. This means this is the type of earthquake that is often felt, but only minor damage. Example 4. Fill in the following blanks to show how the relative intensity of earthquakes of the following magnitudes compare. A. A magnitude 3 earthquake has blank times the relative intensity of a magnitude 2 earthquake. Since we want to know the size of one quantity in relationship to another quantity, we should use comparing division. We will put the larger quantity in the numerator and the smaller quantity in the denominator. Since we are asked to compare relative intensities, we need to convert magnitude to relative intensity before we divide. Recall, relative intensity equals 10 to the magnitude. So the magnitude 3 earthquake has a relative intensity of 10 to the third power, and the magnitude 2 earthquake has a relative intensity of 10 to the second power. Recall from your early days in mathematics that when we are dividing two quantities that have the same base, we are allowed to subtract their exponents. So 10 to the third divided by 10 squared is equal to 10 to the 3 minus 2, or 10 to the 1, which equals 10. Therefore, a magnitude 3 earthquake has 10 times the relative intensity of a magnitude 2 earthquake. Note there is nothing special here about 3 and 2. Had the magnitudes for our earthquakes been 5 and 4, or 7 and 6, we would have done the same process and gotten the same answer. This means if the magnitudes are 1 unit apart, the relative intensity of the larger earthquake is 10 times the larger intensity of the smaller earthquake. Furthermore, if the magnitudes happen to be 2 units apart, for example, a magnitude 4 earthquake and a magnitude 2 earthquake, this procedure would have us take 10 to the 4 minus 2, and we would get 10 squared, or 100, as our answer. That is, if the magnitudes of the earthquakes are 2 units apart. Then the larger earthquake has 100 times the relative intensity of the smaller earthquake. Part B. A magnitude 5.7 earthquake has about blank times the relative intensity of a magnitude 4.3 earthquake. Once again, we will use comparing division to solve this problem. We will take the relative intensity of the larger earthquake and divide it by the relative intensity of the smaller earthquake to find how many times larger in relative intensity the bigger earthquake is when compared to the smaller earthquake. Our first step, once again, is to convert from magnitude to relative intensity. Recall, relative intensity equals 10 to the magnitude. So, the magnitude 5.7 earthquake has a relative intensity of 10 to the 5.7, and the magnitude 4.3 earthquake has a relative intensity of 10 to the 4.3. Since the bases are the same, we could simply subtract the exponents. That is, 10 to the 5.7 divided by 10 to the 4.3 is 10 to the 5.7 minus 4.3. This equals 10 to the 1.4 power, which I understand is less than 10 squared, or 100, and greater than 10 to the first, or 10. When I put this into my calculator, I get approximately 25.12. So the magnitude 5.7 earthquake has about 25.52 times the relative intensity of a magnitude 4.3 earthquake. The reason knowing how to do this conversion is important for the average citizen is that earthquakes are generally reported to the public in terms of magnitude. And a 4.3 earthquake doesn't seem much smaller than a 5.7 earthquake. The difference in magnitude is just 1.4 units. However, after doing this conversion, we can see that in fact, the larger earthquake is about 25 times as intense as the smaller earthquake. This means a magnitude 5.7 earthquake is in a completely different category than a magnitude 4.3 earthquake in terms of damage done and resources needed to help repair the afflicted area.